Have you ever wondered how a site like Instagram or TikTok can handle millions, maybe even billions of photos and videos being uploaded and viewed every single second? It feels like magic, right? Well, the secret behind it all is something called system design. It's the invisible blueprint that lets these massive services work at a scale that's almost impossible to wrap your head around. And today, we're going to pull back the curtain and demystify it together.
So that's the big question, right? How do you actually build something that can serve a billion people all at the same time? It's a monumental challenge. And believe it or not, the answer starts in a surprisingly simple place.
You see, to understand a system with a million computers, we first have to get real about the limits of just one. Because every single problem we're going to face at massive scale, speed, storage, processing power, it all starts right here, with the basic building blocks of one single machine.
Let's think of a single computer like a little workshop. Your disk, that's your giant warehouse in the back where you keep everything for the long haul. Then you've got your RAM, which is like your workbench, holding only the stuff you're actively working on right now. The CPU, that's you, the craftsperson, doing all the actual work. And the motherboard is just the workshop floor that connects everything. The key thing to get is this. Your entire operation is limited by how fast you can get parts from that slow warehouse to your fast workbench. And this right here reveals a fundamental trade-off that is going to echo through this entire explainer. Your disk is a massive warehouse. It holds a ton, but it's kind of slow to get things out of it. Your RAM is your workbench, much smaller, but way, way faster. And cache? That's like the single tool you keep in your pocket. It's tiny, but it's instantly right there when you need it. You always have to make a choice. Do you want massive size, or do you want blinding speed? You can't have it all. And this puzzle is at the absolute heart of everything we're about to build. Okay, so we've got our computer, it's all set up, but a computer sitting by itself in a room is pretty useless. To build a service, we've got to connect it to the internet. And that means it has to learn the rules of the road, the protocols that let all the computers in the world talk to each other.
The very first rule is something called DNS, the Domain Name System. The easiest way to think about it is that it's the internet's phone book. See, we humans remember names, like Google.com. But computers only understand numbers, these long strings called IP addresses. DNS is just the helpful translator in the middle. Without it, you'd have to memorize a bunch of random numbers for every single website you wanted to visit. It's a simple idea, but it's an absolutely critical first step.
So, you've got the address. Now, how are you going to send your package? You basically have two choices. There's TCP, which is like sending certified mail. It's a little slower, but you get a guarantee that every single piece of that web page is going to arrive, and in the right order. Then there's UDP. That's more like sending a postcard. It's super fast, but hey, a piece might get lost along the way. Now that sounds bad, but it's perfect for something like a video call, where you'd much rather have a tiny 1-second glitch than a long frozen screen.
All right, our computer is online, it's talking to the world, and we've launched our app. Things are going great. But then our success becomes our biggest problem. The first 1,000 users are fine, but when a million people all try to connect at once, our poor little server gets completely overwhelmed and it just crashes. This is the first great wall we hit in system design, the problem of scale.
So what's the solution? Well, instead of using one super powerful server, you use hundreds or even thousands, and you put a load balancer in front of all of them. It's exactly what it sounds like. It acts like a traffic cop for the internet, looking at all the incoming requests and smartly directing each car to the lane or server that's the least busy. It's a simple concept, but it's what stops any single machine from getting buried in traffic.
So here's how that works in practice. Your request to see a web page hits the load balancer first. The load balancer instantly checks its whole fleet of servers and asks, okay, who's free? It finds the one that's least busy, forwards your request over to it, and that server handles the job. By doing this millions of times a minute, you can handle an incredible amount of traffic without any one machine even breaking a sweat.
Okay, awesome. We've solved the traffic problem. But in doing so, we've just created a brand new headache for ourselves: data. All those millions of users are creating profiles, posting photos, writing comments. Where in the world are we going to store all of this information? The answer, of course, is a database.
And databases really come in two main flavors. You've got SQL, which is like a perfectly organized filing cabinet. It has strict rules and everything has its place. This is absolutely essential for something like a bank transaction, where you cannot afford a single mistake. On the other hand, you've got NoSQL. This is more like a chaotic brainstorming whiteboard. It's super flexible, a little messy, and it's built to handle enormous amounts of unstructured data, like all the random posts and pictures on a social media site.
So as your data grows, how do you make your database bigger? Well, you've got two basic moves. You can scale up, which just means you buy a bigger, more powerful, and way more expensive machine. But eventually you're going to hit a hard physical limit. You literally can't buy a bigger computer. The other option is to scale out, which means you just keep adding more and more cheaper machines to the group. It's more complex to manage for sure, but this is the secret sauce to achieving that kind of limitless scale we're after.
So our system is amazing. It can handle millions of users, it can store all their data, but now we have a new enemy, the speed of light. Seriously, if your server is in Virginia, but your user is in Tokyo, their request has to physically travel halfway around the world and back again. That's a laggy, slow, frustrating experience. We need to make this thing feel fast for everyone, no matter where they are.
And the key to speed is a clever trick called caching. Hey, remember our whole workshop analogy from the beginning? The warehouse, the workbench, the tool in your pocket? Caching is the exact same idea, but applied to the entire global system. Instead of going all the way back to the slow warehouse, our main database, for every single request, we keep copies of the most popular stuff in a faster, closer pocket. This way, we avoid those long, expensive trips and make everything feel instantaneous. What's really so smart about this is that caching isn't just one thing. It's a multi-layered defense against slowness. The system caches stuff right there in your web browser. Then it caches images and videos on a global network of servers near you, called a CDN. It even caches things right next to the database itself. Each layer acts like a filter, stopping a request from having to make that long, slow journey. It's this combination that shaves off those precious milliseconds and makes an app feel snappy and responsive. Okay, we've done it. We've built a powerful, fast, scalable system, but now we arrive at the final boss of system design. There's a fundamental law, almost like a law of physics for computer systems, that forces us to make a very, very difficult choice. It's called the CAP theorem. The CAP theorem is brutally simple. It says that for any system that runs on more than one computer, which at this scale is all of them, you can promise your users two of these three things: consistency, availability, or partition tolerance. You get to pick two, but you simply cannot have all three.
Now I want to be super clear here. This isn't a suggestion, it's not a best practice, it's a fundamental law like gravity. You are physically unable to build a system that has all three of these properties at the same time. Every single large-scale service you use today has been forced to make a painful compromise right here.
So what do these things even mean? Well, consistency means everyone sees the exact same, most up-to-date data, always. Availability means the site is always online and responsive, no downtime, ever. And partition tolerance means the system keeps working even if the network connecting its different parts gets flaky or breaks. And here's the kicker. In the real world, the network is always flaky. You don't have a choice. You have to pick partition tolerance, which leaves you with one impossible decision. Do you want to be perfectly consistent or perfectly available? You can't be both.
And that brings us right to the core philosophy of system design. It's not about finding some perfect, magical solution. It's about making smart compromises based on what you actually need. A banking system, for instance, will absolutely sacrifice a moment of availability to guarantee that your balance is always consistent. But a social media feed, it might show you slightly old data for a second, sacrificing consistency to make sure the app is always available when you open it.
And there you have it. That's our journey. We started with the humble parts of a single computer and we built up, piece by piece, solving one problem at a time until we had a global system of load balancers, scaled-out databases, and multi-layered caches. And in the end, we learned that every single decision is shaped by that fundamental law of smart compromises, the CAP theorem.
So the next time you open up your favorite app, just think about this for a second. When the engineers were building it, what did they choose? Did they choose perfect, up-to-the-millisecond data consistency? Or did they choose 100% rock-solid availability? Because now you know for a fact they couldn't have chosen both.